Complete mediation. Every access, every time. Opening. The door that never stays open. Here is a question worth sitting with for a moment. When you walk into a secure building using a badge, the door opens. You walk through. The door closes. The next time you want to enter, you badge again. Nobody looks at you and says, "You came in this morning, so you are fine, just walk through." The physical world understands something that computer systems have spent decades getting wrong. The act of granting access in the past says nothing meaningful about whether access should be granted right now. This is the idea at the center of complete mediation, and it is deceptively simple to state. Every access to every resource must be authorized at the moment of access, not at the moment of the last check. The word every in that sentence is doing all of the work. Not most accesses. Not accesses that look suspicious. Not accesses to resources flagged as sensitive. Every access. Every time. The reason this principle is deceptively simple is that it is extremely easy to state and extremely easy to violate without knowing you have violated it. The violation does not announce itself. It shows up as an assumption baked into session management, into protocol design, into how firewall rules are written, into the way a privileged account is provisioned and then allowed to sit indefinitely. The assumption is, we checked and it was fine, so we do not need to check again. That assumption is the precise gap through which an enormous fraction of real-world security incidents have traveled. What makes this principle the technical heart of zero trust is not the technology it requires, is the stance it demands. Complete mediation is a refusal to extend trust beyond the moment of verification. It is an architectural commitment to the idea that authorization is not a state that persists. It is a decision that is remade continuously at every access event. Building that commitment into systems, into protocols, into identity infrastructure, and into the policies that govern all of it. That is what this session is entirely about. The foundation, what access control actually means at the verification layer. Before the principle of complete mediation can be applied to real systems, the vocabulary of access control needs to be precise, because three concepts that are often conflated are in fact distinct mechanisms, each of which operates at a different layer of the authorization decision. Mandatory access control, discretionary access control, and role-based access control are three different answers to the same underlying question. Who has the authority to decide whether a given subject can access a given object? In mandatory access control, that authority belongs to the system itself. Labels are assigned to both subjects and objects by a central authority, and the system enforces access based on the comparison of those labels, regardless of what any individual user or owner wants. The owner of a file cannot grant another user access to it if the label comparison forbids it. This model is the most rigid and the most suited to environments where the sensitivity of data is formally classified and the classification must be enforced absolutely. A defense intelligence environment is the canonical example. An analyst at the secret clearance level cannot access top secret data, even if a colleague sends them a copy of it and invites them to open it. Discretionary access control places the authority with a resource owner. The owner of a file decides who can read it, who can write it, who can execute it. The system enforces the access control list that the owner maintains. This is the model that underpins most file system security on general-purpose operating systems. The Unix permission model and the Windows NTFS-ACL model are both fundamentally discretionary, even though they vary considerably in their granularity. The strength of discretionary access control is its flexibility. Its weakness, in the context of complete mediation, is that a discretionary permission once granted tends to persist. The owner grants access. The access control list records the grant, and unless the owner explicitly revokes it, the access remains indefinitely. Periodic access reviews, the organizational process of auditing who has access to what and confirming that the access is still appropriate, exists precisely because discretionary access control does not revoke permissions automatically when circumstances change. Role-based access control answers the question differently again. Instead of tying permissions to individual users, it ties them to roles, and users are assigned to roles. The finance role can read financial records and write to the accounts payable system. Accountability is the layer that sits on top of all three. Accountability answers a different question, not whether access was authorized, but whether we can prove it. Accountability is achieved through audit logging, the practice of recording every access event with sufficient detail that a subsequent investigation can reconstruct who accessed what, from where, at what time, and with what result. The audit log is the evidentiary trail that makes complete mediation verifiable rather than merely aspirational. An organization that checks authorization on every access but does not log the results has no way to detect the case where the check was bypassed, no way to prove compliance, and no forensic foundation for incident investigation. The distinction between stateful and stateless protocols is the final foundational concept, because it shapes the architecture of complete mediation at the network layer. A stateful protocol maintains context across multiple interactions. TCP is stateful. The connection carries sequence numbers, acknowledgement numbers, and window sizes that the sending and receiving system maintain across every packet in the session. A stateless protocol treats each interaction as independent, with no memory of previous exchanges. HTTP in its original design is stateless. Each request stands alone, and the server has no inherent memory of prior requests from the same client. This distinction creates different challenges for complete mediation. In a stateful session, the authorization decision made at session establishment can be inherited by every subsequent packet, which is exactly what a stateful firewall does, and exactly where the vulnerability lies when session state is not synchronized with the current state of the identity provider. In a stateless protocol, each request must carry its own credential, which is why every API call must present a token, and why the API gateway must validate that token on every request rather than relying on a session established by a prior request. The structural tension, verification versus velocity. Every principle in security contains a tension, and the tension inside complete mediation is particularly direct. It is the tension between verification and velocity. Continuous authorization checking requires a round trip to an authoritative source. That round trip takes time. For an SSH session where every command triggers a check against Active Directory, the latency is measured in milliseconds, but in a high-frequency environment, milliseconds accumulate. For a web application where every page load requires a token validation call to an identity provider, the latency is one of many factors contributing to page load time. For a microservices architecture where each service call requires mutual TLS verification and a policy engine query, the cumulative latency across a chain of 10 services can become significant enough to affect the end user's experience. The velocity side of the tension is not merely about user convenience, though that matters for adoption. In operational technology environments, factory floors, power generation facilities, hospital systems, latency in a control system is not a performance annoyance. It is a safety constraint. A SCADA system that controls a physical process cannot tolerate a delay that puts the control loop out of phase with the physical system it is managing. The security principle does not disappear in these environments. It is redesigned to fit the constraint. The resolution of this tension is never a choice between complete mediation and no mediation. It is always a choice about the granularity and frequency of mediation, and the consequence of that choice must be made explicit and owned by someone with the authority to accept the residual risk. The organization that implements 5-minute cache token validation has not abandoned complete mediation. It has made a conscious, documented decision that 5-minute staleness is an acceptable trade-off given the performance constraints and the threat model. The organization that implements 5-minute cache tokens without documenting the decision, without reviewing it periodically, and without connecting it to any threat model has simply inherited a vulnerability by accident. This is where the principle connects to governance. Complete mediation without governance around the granularity decisions produces exactly the kind of implicit trust assumption that the principle is designed to eliminate. The SSH session that persists through a termination event is not a technical failure. It is a policy failure. The policy did not address what happens to live sessions when account status changes. The technology faithfully implemented the policy that existed. The gap was in the policy. Architecture, building continuous authorization into real systems. The architectural expression of complete mediation is the policy enforcement point. The technical component whose exclusive job is to intercept every access request and verify against the policy engine whether the access is currently authorized. The policy enforcement point does not store state about previous decisions. It does not assume that a request from a user who was authorized 5 minutes ago is still authorized. It asks, for each request, is this subject, in this context, currently authorized to perform this action on this resource? Zero Trust Network Access represents the most complete modern architectural expression of this principle. In a ZTNA architecture, the network is not a trust boundary. There is no inside the network where things are implicitly trusted. Instead, access to each application is individually brokered by an identity-aware proxy. The user authenticates to the identity provider, presents device posture attestation, and requests access to a specific application. The policy engine evaluates the request against multiple dimensions simultaneously: identity attributes, device health, time of day, geographic location, threat intelligence signals, and a sensitivity classification of the application being requested. If all dimensions pass, the proxy grants a time-limited connection to that specific application, not to the network, not to adjacent systems, not to anything the user did not specifically request. The per-application granularity is architecturally significant. Traditional VPN access grants network-level access. Once connected, the user can reach anything on the network that their firewall rules permit. Per application, ZTNA access grants nothing beyond the specific resource the policy permits at the specific moment of the request. An attacker who compromises a ZTNA session has compromised access to one application for the duration of the token's validity. An attacker who compromises a VPN session has compromised network-level access to everything reachable from that network segment for the duration of the VPN session. Just-in-time privileged access is the application of this same principle to the specific problem of standing privileges. A standing privilege is the antithesis of complete mediation. It is an authorization decision made at provisioning time that persists indefinitely until someone explicitly revokes it. A database administrator with standing root-level access to a production database has that access at 3 a.m. on a public holiday when nobody is watching, has it when they're disgruntled, has it when their credentials have been compromised. Just-in-time access removes the standing privilege entirely. When the administrator needs to perform a task, they request access through a privileged access management platform, specify the task, obtain approval through a workflow, receive time-limited elevated credentials, perform the task, and the access expires automatically when the window closes. The authorization decision is made at the moment of need, not at the moment of provisioning. The mediation is complete because there is nothing to revoke. The access never persisted in the first place. The TLS handshake is the cryptographic expression of complete mediation at the transport layer, and it is worth examining precisely because it is so fundamental that it is often taken for granted. When a client connects to a server over TLS 1.3, neither party trusts the other based on prior history. The handshake establishes fresh cryptographic proof of identity and agreement on session keys for every new connection. The server presents its certificate. The client validates the certificate chain against its trust store. The parties perform a key exchange using ephemeral Diffie-Hellman parameters, and a unique session key is derived that has never existed before and will never exist again. This is complete mediation at the connection layer. Every new connection reestablishes trust from cryptographic first principles, with perfect forward secrecy ensuring that even if a private key is compromised in the future, past sessions cannot be decrypted. Configuring a web server for TLS 1.3 properly means eliminating the cipher suites and protocol versions that permit session resumption in ways that compromise this property. TLS session resumption, in its earlier implementations, allowed a client to present a session ticket that resumed a prior session's cryptographic state without repeating the full handshake. This is a deliberate performance optimization, and it trades some of the completeness of mediation for connection speed. In a threat model where session ticket theft is a realistic concern, the trade-off favors full re-handshake. In a threat model where connection latency to authenticated clients is the primary concern, session resumption with short ticket lifetimes may be the appropriate balance. Tools that enforce mediation at every layer. For tools enforce complete mediation across different surfaces, and each one reveals something different about what the principle demands in practice. A stateful firewall enforces complete mediation at the packet level, and it does so through a mechanism called session state tracking. When a TCP connection is established, the firewall records the session in its state table: source IP, destination IP, source port, destination port, protocol, and the current state of the TCP handshake. Every subsequent packet in that connection is checked against the state table. A packet that does not correspond to a known, established session, a SYN that arrived without a preceding SYN, a RST on a connection that was never established, a packet with flags that are inconsistent with the claimed session state, is dropped. This prevents out-of-state packet injection attacks, where an attacker crafts packets that the receiving system will process as part of a legitimate session that the attacker was never actually part of. The limitation of the stateful firewall is that it mediates at the network and transport layer, not at the identity layer. It knows about TCP connections. It does not know about users. A stateful firewall that sees a connection from an authenticated user's IP address and port to a permitted destination will pass the traffic without any awareness that the user who established the connection an hour ago has since been terminated and their laptop has been handed to the next person. The firewall state table says established, and it passes the packets. Complete mediation at the identity layer requires a different component. A cloud access security broker continuously monitors cloud application sessions at the identity and behavior layer, which is precisely where the stateful firewall has no visibility. When a user authenticates to a cloud application, the CSB brokers the session, maintaining awareness of who the user is, where they're authenticating from, what device they're using, and what actions they are performing within the application. The CSB applies behavioral policies in real time. If the user's authentication location changes from Mumbai to London within a 2-hour window, the CSB detects the impossible travel signal and can immediately challenge the session with a step-up authentication requirement or revoke it entirely. The access that was authorized at session establishment is re-evaluated continuously against signals that were not available at the moment of the original check. The cost of this continuous evaluation is infrastructure complexity and the operational overhead of tuning behavioral policies. An impossible travel policy that does not account for VPN usage will fire constantly on employees who authenticate through a VPN endpoint in a different city. An anomaly detection policy that is set too aggressively will generate enough false positives that the SOC team begins ignoring the alerts, which is the precise failure mode that turns a security control into theater. The CAS value depends entirely on the quality of the behavioral policies and the operational commitment to reviewing and tuning them as the organization's patterns evolve. An API gateway enforces complete mediation at the application programming interface layer, which has become one of the most consequential surfaces in modern application architecture. Every API call carries a JSON web token, a cryptographically signed assertion of the caller's identity and the permissions they hold. The API gateway validates this token on every request, checking the signature against the issuing authority's public key, checking the expiration time, checking the audience claim to confirm the token was issued for this API, and checking the scope claims to confirm the caller is authorized for the specific operation being requested. The security property this provides is that authentication is not a one-time gate at session establishment. An API session that was authorized an hour ago cannot simply continue making requests if the token has expired or if the user's permissions have been revoked in the identity provider. The gateway's per-request validation is the enforcement mechanism. The cost is computational. Every request incurs the overhead of cryptographic signature verification. In high-throughput API environments, this is a real engineering concern. managed through hardware acceleration, token caching with short TTLs, and pre-validated certificate chains that eliminate repeated certificate fetching. The limitation is that token validation only catches revocation events that occurred before the token's expiration. A token issued with a 1-hour lifetime may continue to validate for up to an hour after the underlying permissions were revoked. Reducing token lifetimes reduces this window at the cost of more frequent reissuance load on the identity provider. Multi-factor authentication session timeouts are the user-facing expression of complete mediation, and they are where the tension between verification and velocity is felt most immediately by end users. A session that requires re-authentication after 15 minutes of inactivity is significantly more secure than one that persists for 8 hours. An attacker who finds an unattended workstation with an active privilege session has, at most, 15 minutes before the session requires fresh credentials. An attacker who finds an unattended workstation with an 8-hour session has, at most, the remainder of the working day. The design response to user friction from session timeouts is not to lengthen the timeout. It is to make re-authentication fast enough that it is not materially disruptive. Biometric re-authentication, a fingerprint or face scan, requires less than a second. A hardware security key requires a single touch. The friction of a 15-minute session timeout with biometric re-authentication is far lower than the same timeout with a password entry, and the security benefit is identical. Two implementation scenarios demonstrate the gap between designing for complete mediation in theory and making it function in the moments that matter most. The first is the ZTNA deployment for a hybrid workforce. The starting point for this implementation is identity and device inventory. You cannot implement per application access control if you do not have an authoritative inventory of which users should have access to which applications and under what device conditions. Before any technical configuration begins, the implementation requires a data gathering phase, working with application owners to document who legitimately needs access to each application, what device hygiene requirements are appropriate for applications of different sensitivity, and what the current access patterns look like so that the policy can be validated against reality rather than against assumptions. The identity-aware proxy configuration follows. For each application, a policy is defined that specifies the conditions under which access is granted. The user must be a member of a specific group in the identity provider. The device must have a current antivirus signature database and full disk encryption enabled. The access must occur during business hours unless an exception is approved. And the geographic location must be consistent with the user's normal working locations or a currently active VPN session. The proxy enforces these conditions on every access request. It does not enforce them once at login and then trust the session for the rest of the day. The device posture check deserves particular attention because it is the element that most deployments underinvest in. A user who authenticates strongly with MFA but whose device is running 2-month-old antivirus signatures and has a critical unpatched vulnerability is not a low-risk access subject. Device posture attestation integrates the endpoint management platform with the policy engine so that the policy can query the device's current patch level, configuration compliance state, and threat detection status at the moment of the access request and use those signals in the access decision. A device that was compliant yesterday but acquired a piece of malware overnight fails the posture check this morning and is denied access until it is remediated. The just-in-time privileged access implementation for a team of database administrators begins with the deliberate removal of standing access, a step that is technically simple and organizationally uncomfortable. The database administrators who have been provisioned with standing root-level access to production databases will raise legitimate concerns about operational impact. What happens if they need access at 2 in the morning when the approval workflow cannot be completed quickly enough? The implementation must address this concern before it removes the standing access, or the implementation will be reversed under operational pressure the first time it creates a genuine incident. The answer to the 2 in the morning concern is a break glass mechanism. Break glass accounts are emergency access credentials stored in a physically secured location, a sealed envelope in the safe, a credential vault with a hardware key that can be accessed by any senior engineer in a genuine operational emergency, with every access logged and reviewed by the security team the following business day. The existence of a well-documented, well-tested break glass procedure is the organizational prerequisite for removing standing access, because it demonstrates that the removal does not mean that access is unavailable in an emergency. It means that accessing it in an emergency is auditable and visible in a way that standing access is not. With the break glass mechanism in place and tested, the standing access is removed. Database administrators request access through the Privileged Access Management Platform, specifying the task they need to perform and the system they need to access. The request triggers an approval workflow that routes to their manager or to an on-call security engineer, depending on the time and urgency. Approval grants a time-limited credential, typically the estimated duration of the task plus a small buffer, that is injected by the PAM platform directly into the connection rather than being revealed to the administrator. The administrator cannot copy the credential, cannot extend its validity, and cannot use it for any system other than the one specified in the request. Every command executed during the session is recorded by the PM platform's session proxy. When the time window expires, the credential is rotated automatically and the session is terminated. When complete, mediation fails, diagnosing the gaps. 3 failure scenarios surface the specific mechanisms by which complete mediation breaks down, and each one has a different diagnostic path and a different architectural implication. The first scenario is the user who receives a permission-denied error on a resource they accessed successfully yesterday, with no plan changes to their access or to the resource. The instinct is to check whether their access was revoked and restore it, but that instinct skips the diagnostic step that matters most. The first question is not whether the access was revoked. The first question is whether the access should have been revoked, and if so, why. The diagnostic begins by pulling the identity provider's audit log for this user's account in the relevant time window. The second scenario is the investigation that follows an alert. A CM rule fires for multiple failed SSH authentication attempts from a foreign IP address, followed by successful authentication using a legitimate key pair. The user claims they were not traveling and did not initiate any SSH sessions. This is a complete mediation failure in the most significant possible sense. The SSH protocol performed its authentication check correctly. The key was valid, the check passed, and access was granted. But the access was not authorized in any meaningful sense. The legitimate key was being used by someone who was not the legitimate key holder. The investigation begins at the credential layer. How was the private key obtained? Pull the user's workstation log for the 48 hours preceding the incident, looking specifically for connections to external file transfer destinations, USB device events, clipboard access to the SSH key file, phishing email interactions, and any process that accessed the SSH keys file location. If the workstation had malware, the malware may have exfiltrated the private key directly. If the workstation did not have malware, the key may have been obtained through a public source. A private key accidentally committed to a code repository is a distressingly common source of key compromise. The parallel investigation examines the SSH session itself. Pull the full session log from the destination server. What commands were executed during the session? Did the attacker establish persistence? A new authorized key added to the user's authorized_keys file, a cron job created, a reverse shell planted? Map the timeline of commands against the MITRE ATT and CK framework. What TTPs are visible? This mapping tells you whether this was an opportunistic access or a targeted intrusion with a specific objective. The architectural implication of this scenario is that key-based authentication, while stronger than password authentication, does not by itself constitute complete mediation. The key validates possession of a credential. It does not validate that the entity possessing the credential is the legitimate user in the current context. Enriching SSH authentication with contextual signals, certificate-based authentication that binds the key to a specific identity provider identity, with conditional access policies that evaluate geographic location and device health before granting the session, would have caught the impossible travel signal and terminated or challenged the session before the attacker could execute. The third scenario is the SOC analyst alert that fires consistently for a known IP range that hosts both legitimate residential proxy services and a subset of attacker infrastructure. The alert is designed to flag access attempts from this ASN because attackers have been observed using residential proxies to evade geo-blocking. The alert is also firing on legitimate employees who use residential ISPs in that ASN for home working. The diagnostic is a signal decomposition problem. The single signal access attempt from ASN X is insufficient to distinguish between the two populations. Three roles encounter complete mediation at different depths, and the sophistication each brings to it determines whether the principle is engineered properly, detected accurately, or responded to with genuine containment rather than procedural theater. The security architect encounters complete mediation at design time, specifically at the moment when they are asked to evaluate whether an existing application can be brought into a ZTNA architecture. The application in question is 15 years old, written against a proprietary authentication framework that predates OAuth and maintained by a vendor who is not willing to refactor the authentication layer. The architect's task is to determine what level of mediation is achievable without modifying the application itself. The trade-off the architect must document is the residual gap. The proxy can mediate access to the application, but it cannot mediate individual actions within the application. Once a request is forwarded, the application's own session management takes over. If the application grants a session cookie with a 4-hour validity and does not support 4-session termination through an API, The proxy cannot revoke mid-session access after the initial request is authorized. The architect documents this gap, the threat it represents, and the organizational acceptance of the residual risk with a compensating control recommendation: aggressive session timeouts, aggressive network-level session termination capability, or an accelerated timeline for replacing the legacy application. The SOC analyst at L2 and L3 encounters complete mediation in the investigation at the exact moment where an alert about a successful authentication that follows failed attempts requires a judgment call about whether the mediation that occurred was genuine or manufactured. The junior analyst who escalates this alert as a confirmed compromise has made the error of treating the technical observable, failed attempts followed by success, as a verdict. The analyst's investigation methodology moves through these interpretations in sequence, adding context with each step: source IP reputation and history, device identity and enrollment status, geographic plausibility relative to the user's recent authentication history, the timing relationship between the failed and successful attempts. A brute force typically has a programmatic cadence, while a forgetful user has irregular timing with longer gaps. The commands or actions taken after the successful authentication. A legitimate user's first action after login is recognizable from their behavioral baseline, while an attacker's first action often includes reconnaissance commands that no legitimate user in that role would typically execute. The security automation engineer encounters complete mediation at the automation layer in the design of the stateful alert deduplication system. The problem being solved is straightforward. The same IOC should not generate a new ticket within 24 hours if it has already been actioned. The implementation challenge is that the deduplication logic must itself practice complete mediation. It must check the current state of the IOC at the moment of each new alert, not rely on the state recorded when the IOC was first seen. The design that fails is one that stores the IOC in a scene set and suppresses all subsequent alerts matching that IOC for 24 hours, regardless of the severity or context of subsequent matches. This implementation creates the precise vulnerability it was designed to prevent. An IOC that was low severity when first seen is now suppressed, even when it reappears in a high-severity context. The deduplication logic practiced complete mediation on whether the IOC was seen, but it did not mediate on whether the suppression decision that was valid for the first alert is still valid for the subsequent one. The design that succeeds checks three things at the moment of each new alert: whether the IOC has been seen before, what the severity of the current alert is compared to the severity of the previous alert for the same IOC, and whether the current alert's context, the affected asset, the attack chain it is part of, the time frame, is consistent with the context of the prior alert or represents a new and distinct event. An IOC that was seen as part of a low-severity scan 12 hours ago, but now appears in a lateral movement alert involving a domain controller is not a deduplication candidate. It is a severity escalation that should bypass the suppression logic entirely and generate a high-priority alert regardless of the 24-hour window. Case scenario: the developer who would not leave. Here is the scenario in full, with a constraint that makes it instructive rather than obvious. A financial services firm runs a cloud-hosted trading platform. The platform has 12 Linux-based production servers that are accessible via SSH to a team of 8 senior platform engineers. The SSH access is managed through individual key pairs. Each engineer has a private key on their workstation, and the corresponding public key is stored in the authorized_keys file on each server. There is no central identity provider integration for SSH. The SSH access list is managed manually by the infrastructure team lead, who adds and removes authorized keys when engineers join or leave the team. On a Tuesday morning, one of the senior engineers, call him the developer, is placed on administrative leave pending an investigation into unauthorized access to client data. HR notifies the security team at 9 in the morning. The security team disables the developer's Active Directory account, which revokes his access to email, the Jira project management system, the CI/CD pipeline, and the code repository. His laptop is collected. His building access badge is deactivated. The constraint is this. The infrastructure team lead who manages the SSH authorized_keys files is at a conference in another time zone. The conference runs until 6 in the evening. It is currently 9:15 in the morning. At 10:30, the security team discovers that the developer's SSH session, established at 8:45 that morning from his home workstation, before the account was disabled, is still active on 3 of the 12 production servers. The developer has been aware of the investigation since 9:15, having been informed by a colleague before HR reached him. He has nearly 2 hours of unmonitored access to production trading infrastructure. The immediate containment action is network-level session termination. The network team identifies the TCP sessions corresponding to the developer's home IP address and issues a RST from the perimeter firewall, terminating the connections within seconds. This is an emergency measure that does not require the infrastructure team lead's involvement and does not depend on the SSH authorized_keys management process. It is blunt. It terminates all connections from that source IP, which may include legitimate connections if the developer is sharing a home network, but it addresses the immediate risk. The post-incident investigation reveals 3 architectural failures, each of which represents a violation of complete mediation at a different layer. The first failure is the absence of identity provider integration for SSH authentication. The key pair authentication model does not check the user's account status against any authoritative source at the moment of each command. It checked once when the session was established and then extended trust for the session's duration. The fix is SSH certificate-based authentication backed by a short-lived certificate authority. Instead of static key pairs, the engineer's workstation requests a certificate from the certificate authority at SSH connection time. The CA checks the engineer's account status against Active Directory before issuing the certificate. The certificate has a validity period of 8 hours. It expires at the end of the working day and must be renewed for each new working session. When a developer's AD account was disabled at 9 in the morning, any subsequent request for a new SSH certificate from his workstation would have been denied. Sessions established before account disablement continue until the session ends naturally, but the certificate's short validity period and the PAM integration with the CA mean that the session's validity can be revoked by revoking the certificate. The second failure is the absence of a privileged access management platform that brokers SSH sessions through a proxy. In a PAM-brokered SSH architecture, the engineer does not connect directly to the production server. They connect to the PM platform's session proxy, which authenticates against the identity provider, checks the account status and any active holds, and then establishes the connection to the production server on the engineer's behalf. The PM platform can terminate any brokered session immediately, without requiring changes to the target server's authorized_keys file, and without requiring network-level intervention. When the security team received the alert at 9:15, the PAM platform administrator could have terminated the 3 active sessions in under 30 seconds from the PAM console. The third failure is the manual, person-dependent authorized keys management process. A security control that depends on a specific individual's availability to function is a single point of failure by design. The fix is a centralized authorized keys management system, a configuration management tool that pushes authorized keys files to all production servers on a schedule, drawing from a managed identity store. When an engineer is removed from the identity store, the configuration management run on the next cycle removes their public key from every authorized keys file across the fleet. The cycle can be triggered manually in an emergency, producing a revocation event within minutes rather than hours. The 3 fixes together implement complete mediation at every layer. The certificate authority mediates at session establishment. The PAM proxy mediates at session level with real-time revocation capability, and the centralized key management mediates at the authorized_keys level with automated, continuous synchronization to the identity store. The system no longer depends on the availability of a single administrator, and access is no longer permanent. It is a continuous negotiation that can be interrupted at the moment the authorization state changes. The trade-off that the security team documents in the post-incident report is the performance and availability dependency introduced by the certificate authority integration. The CA is now in the critical path of every SSH connection. If the CA is unavailable, maintenance window, network partition, infrastructure failure, engineers cannot establish new SSH sessions to production servers. The mitigation is a highly available CA deployment with geographic redundancy and a documented break glass procedure for emergency access when a CA is unavailable. The break glass access is fully logged and reviewed, ensuring that even the emergency path is mediated, just through a different mechanism. Closing, the authorization that never rests. There's a phrase that experienced security practitioners use when they want to describe the disposition that complete mediation demands. They call it continuous distrust, not paranoia, not obstruction, but the professional refusal to let a prior authorization decision do work it was never designed to do. Every authorization decision is a point-in-time answer to a point-in-time question. Given what we know right now about this subject, in this context, with this device, requesting this resource, should access be granted? That answer is valid for exactly as long as the conditions that produced it remain unchanged. When user's account status changes, the answer is potentially different. When the device fails a posture check, the answer is potentially different. When the geographic location produces an impossible travel signal, the answer is potentially different. The answer does not age gracefully. It does not remain true because nobody has explicitly declared it false. This is what distinguishes systems designed around complete mediation from systems designed around perimeter trust or session-based trust. Perimeter trust says, the user entered through the gate, so they are trusted inside. Session-based trust says, the user authenticated when the session began, so they are trusted for the session. Complete mediation says, The user authenticated at the moment of access, so they're trusted for this specific access event, and the next event will be evaluated fresh. The practical consequence of this stance is that revocation becomes fast and reliable, because the authorization infrastructure is already designed to make continuous decisions rather than to persist historical ones. The terminated employee whose SSH session is killed within seconds, the compromised account whose cloud sessions are revoked the moment the identity provider processes the disable event, the device that is quarantined the moment the endpoint management platform detects malware. These are not exceptional emergency responses. They are the normal operation of a system that was built to redecide at every access event. The security professional who internalizes this principle does not ask whether access was granted. They ask whether access should be granted right now, under current conditions, for this specific request. That is a harder question to answer consistently at scale. It requires investment in identity infrastructure, in device management, in policy engines, in continuous authorization protocols. It requires governance that makes the granularity decisions explicit and owned. It requires operational discipline in reviewing and tuning the behavioral policies that feed the authorization engine. But it is the only question that access control was ever really supposed to answer. Everything else is an assumption waiting to be violated. End of session, complete mediation, every access, every time.